Our next speaker is Liberti, and he will speak about enriched locally generated categories.
Thank you, and thank you for having me today. Can I start? Thank you for having me today. So the title of the talk is Enriched locally generated categories, and let's start. So I should say at the beginning that this is a joint work with Ishiro Sitsuki, and you find it already on archive. In fact, it's on archive since quite some time. And so what's the menu for today? So the first thing I will talk about is the notion of locally M-generated category. And then I will give a sketch-like presentation of those, and this will be the notion of nest. And then I will generalize it to enriched categories, and then I will give an application to Banach Spaces. I should mention we have other applications. I just needed one example. And another application I like can be given to compact Hausdorff spaces, but maybe we will comment on that later. So for the general plan is to introduce a new notion of generated categories and then sketches for them. But before, let's start from something that people know quite well, which are locally presentable categories. And a locally presentable category is a co-complete category with a set of kappa presentable objects, such that every object is a kappa directed colimit of those. And this notion has had quite some fortune in its life, and people use it. And maybe, let's say that it's also easy to check whether a category is locally presentable, because it's enough to check that it is complete and that it has a strongly generating set made of kappa presentable objects. And the second condition is very easy to check when it's true, of course. And people like locally presentable categories. Let's try and say why. Well, because there are many examples in nature, so this is good in general. And they are a general context, but a quite tame one. And they are tame because they have the small object argument, which implies, among the other thing, Christ's version of the adjoint counter theorem. So that's kind of why we like them. Maybe you like them for other reasons. I don't know. So trade-offs. So all in all, they are an efficient place to do some mathematics, not precisely all of it, but some. And let's see some examples. Oh, sorry, let's focus for a moment on what's a locally finitely presentable category. And let me stress on the word finite here. So it is a co-complete category, as I said before. It has a set of finite objects for some notion of finite or compact, some people say. And those generate via directed coordinates. Let's see some examples. Okay, the category of sets is an example, luckily. And here, finite objects are finite sets, as one can expect. And then another case is the category of groups, where we have finitely presentable groups. And there are many examples of this kind, like finitely presentable modules in the case of the category of modules, and stuff of this kind. And then maybe Banach spaces with Lipschitz operators. Well, if they are, then the natural notion of finite object should be finite dimensional Banach space, right? I guess we all agree, except that they are not finitely presentable, so they are not finite. And the meaning, the sense of this talk, if you want, is that there are some concrete instances where we have finite objects in a very intuitive sense, and we want to acknowledge that they are finite and they are cute inside our category, but we need a notion to say that. So, is finite presentability the right notion of finite? And the answer for me is no, because finite dimensional Banach spaces are not finitely presentable. And they are not finitely presentable even in an enriched sense for sensible notions of enrichment. It doesn't matter if you don't know what it means. The fact that we have negative answer is enough in this talk. So we would like to fix this. We would like to find a notion such that they are finitely presentable in some sense. And so you open the literature and you start saying maybe people thought about it. And of course, people thought about it. And you go directly back to Gabriel and Ulmer, and they introduced the notion of locally generated category. And what's the difference? Well, the difference is in the definition of finitely presentable objects, which is that the on functor preserves directed colimits of monomorphism. You see, this is different from the notion of of finitely presentable, because I had to add of monomorphism in the definition. And in this case, you discover that a finitely generated module is a finitely generated module. And the same for groups in the way algebraists would define it. So this notion is not bad. I kind of like it, but it still wouldn't answer my question. Those are not precisely finitely generated in this sense. Okay, so but let's see the definition of locally generated category, because this is where we take our inspiration. So it is a co-complete category with a strong generator formed by lambda generated objects. And then I need to add this assumption, which is that the class of strong quotients is a set. But please look at it as a kind of a set theoretic or a niceness assumption, which doesn't have a conceptual meaning. It's just we need it to make the things work. And theorem of Adamek-Rositsky, a category is locally generated if and only if it's locally presentable. So what am I doing here? Well, to be precise, locally lambda presentable implies locally lambda generated, and the vice versa is false. So as frameworks, they are equivalent, but it's not true that locally lambda generated and locally lambda presentable are the same. So a locally lambda generated category is going to be locally me presentable, but I have to change me. In particular, it's true that finite dimensional Banach spaces are Aleph1 presentable, but then I should say that their cardinality is in some sense Aleph1, and I don't like it. So if you like it, you are fine. But for me, it's not okay. So let's go back to Banach spaces. So there is this theorem by Adamek and Rositsky. Rositsky mentioned it yesterday, and he said, well, a Banach space is a finite dimensional Banach. If you take a finite dimensional Banach space and you take the on functor, then this preserves directed colimits of isometries. If I take the functor into CMET. So now you see that in order to make everything work, I should extend the theory of locally generated categories to something which is more general than monos. I need something to replace isometries. And then I should also enrich it, right? Because I'm using metric spaces here. So that's what we did in the paper. How much time do I still have? Oh, that's perfect. No. I have stuff to say, I just wanted to know. Okay. So let's see the definition of locally generated category. Let's see the definition. You do not have enough information to process it, but then we process it together, okay? So the definition is, it is a co-complete category with a factorization system, which is lambda convenient. And this is the first thing we comment on. What means for a factorization system to be lambda convenient. And then it is a set of lambda generating objects with respect to M. And I think you already see what's going to be the definition, but we will see those. Such that every object is a lambda directed colimits of objects in A and morphism in M. You see, I'm just taking the definition of locally presentable and weighting it, in a sense, along the factorization system. So what is this definition? Well, I should say what is a lambda convenient factorization system to make it sensible. Then I should tell you what is a lambda generated object. And maybe I should also tell that a similar notion, but I would say a little bit different in spirit, has appeared, was already discussed by Adamek and Rosicki in a very old paper. So what's a lambda generated object? It's precisely what you expect. You take the on functor into set, and you ask it to preserve lambda directed colimits of morphisms in M, where M is my class of, let's call them monos, but of course it's just an orthogonal factorization system here. And what does it mean to be convenient? So the notion of convenient is natural, even though it looks technical. So it is a factorization system such that the class of APs, when you fix an object, after all, is just a set, so it's co-well powered. And you see this mimics the same problem that there was also in the case of both locally generated categories. And so you only have a set of strong quotients. And the other one is that M is closed under lambda directed colimits. So for example, it means that a lambda directed colimit of monos is still a mono. And this is true, for example, in modules and in groups, and in fact, in most of the categories you can think of. Even, and this is one of my favorite examples, if you take a directed colimit of closed embedding of compact Hausdorff spaces, this is still a closed embedding. And this is where one can manage to characterize compact Hausdorff spaces in this way. And this is just what truly means to be closed under directed colimits when you spell out. You have to say that the factorizing morphism is in M to be precise. So let's see a couple of examples, only trivial because I have no time. And then I will concentrate on Banach spaces, which is my storytelling example, let's say. So when I choose as a factorization system the stupid one, then to be lambda generated is the same of being lambda presentable, of course, but this is not surprising. So this strictly generalizes local presentability, so presentability, let's say. And if I choose strong AP mono, then lambda generated recovers precisely the notion of Gabriel and Ulmer. And let's see examples of locally generated categories. Well, in this way, you get precisely locally presentable and also locally generated in the sense of Gabriel Ulmer. So this notion sounds okay. It's at least it generalizes what's known in a same. Oh, by the way, notice that this framework instead doesn't generalize this one. So this really encompasses both in the same thing. Okay, so I introduced you to the notion of locally M-generated category, and I gave you some motivations. Now I would like to discuss a notion of a sketch-like notion of presentation. This means I'm going to talk about axiomatization of categories, or really depends what's your background here, but my background is more logical, so for me, this means that I will speak about theories. So the motto here is that if we go back to locally presentable categories, categories with finite limits, they offer categorical presentation of essentially algebraic theories. And if you try to state a theorem, this is the theorem, that you have here K, a locally finitely presentable category. This is precisely the category of Lex functors from K omega up into set, where K omega is the full subcategory of finitely presentable objects. This was already mentioned in the talk of yesterday by Frey. And okay, if you are used to the theory of locally finitely presentable categories, you know this result very well. So, of course, this makes sense because that category has finite limits, right? Otherwise, it makes no sense. And we wanted a similar result for locally generated categories. And that's what I'm going to talk about. And this is the notion of Lambda Nest. So what's a Lambda Nest? It is a category which has lambda small limits. You can concentrate on the finite case, of course. Sorry. And then it must have multiple pullbacks of M morphisms. So it means that it has pullbacks, but then you can keep doing pullbacks and pullbacks and pullbacks, and you still have them. Here I have spelled out the definition of multiple pullback, but maybe if you want, you can see the slides after my talk to check out what it means. So this is the notion of nest, and a model of a nest is a functor into set preserving lambda small limits and multiple pullbacks of M morphism. Notice that this is very similar to the notion that yesterday Jonas Frey told us. Just in his case, he didn't have multiple pullbacks, and in his case, there was no factorization system, just M display maps, right? Then theorem, if you take K EM to be a M locally finitely generated category, then this guy, which is precisely who should be, right, has a structure of omega nest, and the factorization system is precisely induced by the factorization system on K. This is reminiscent of a very old fact in algebra that if you take a strong quotient of a finitely presentable object, then this is finitely generated. So that's more or less what I'm saying. And then, oh, this is cut, but I guess you can guess the theorem that if K is M locally finitely generated, then this is precisely the category of models of its nest, which is what I would call the relevant piece of Gabriel-Ulmer duality for this context. And in the paper, we offer a full Gabriel-Ulmer duality, which I will not discuss today, but we have it in the paper. And yeah, that's precisely what I just said. Okay, so now I should say something about how to generalize it to enriched categories, right? So we are lucky enough because the notion of factorization system, when our category is enriched but is co-complete, doesn't change that much. This is due to the work of Lucy Sheen Wright, I would say. So a factorization system in enriched categories, when it is tensored enough, is just a lambda convenient factorization system in the underlying category. So you don't really see the enrichment in the notion of convenient enriched factorization system. Everything is underlying. And then you can give the definition precisely the way you expect. So I will not comment. Just the on functor in the enriched sense should preserve the right colimits, and then everything is as you expect. And also the definition of a enriched category is the same. And you can do the same for the theory of nests. You can present an enriched notion of nest, when V is locally lambda presentable, so we have to make an assumption on the base in order to recover Gabriel-Ulmer duality. And the assumption is an assumption I don't like because I have to put lambda presentable, not lambda generated with respect to some factorization system. So there is a kind of mismatch there between the two theories that I personally don't like. But it is what it is. Then, in this case, if V is, assume V is locally lambda presentable as a monoidal closed category, then, and if K is the enriched M locally lambda generated, then you still get the relevant part of Gabriel-Ulmer duality, which is, it is the category of models of the nest associated to it in the natural way. I'm finishing, don't worry. And again, we give also the full Gabriel-Ulmer duality in this case. And now we go to the last part. I should say something about Banach spaces. And this is where that mismatch will play a role, which is a bit irritating, but the theorem is good. So let's go back to Banach spaces. And here I'm just keeping the theorem just to keep it in mind because there is a lot of data. So complete matrix spaces is a monoidal closed category. So it's some enrichment. And then the category of Banach spaces is enriched over it. So we have also that. And then dense map isometries is a finitely convenient factorization system in BAN. So this is also good. And then last one, finite dimensional Banach spaces are a strong generator made of lambda generated objects with respect to isometries. Notice that the last one is precisely the theorem I was mentioning at the beginning of the talk. So everything seems to work fine, right? So BAN is locally finitely generated. Not that trivial, because CMAT is not finitely generated as a closed category. So I cannot apply Gabor-Ulmer duality. But then you sit down and check very carefully, and the theorem works in this case. So we have a nest, which is made of finite dimensional Banach spaces, finally, which are finite in this sense. And the models of this nest are precisely Banach spaces, which is what I wanted to say. Now, the good news, this is not in the paper because we noticed it after the paper was released, but it will be in the second version at some point. You can do the same with compact Hausdorff spaces in the category of, what's the name? Compactly generated spaces, that's the name. And the name changes depending on the people that speak about this category. But the point is that finally, we can say that compact spaces are finite. And people have been using this intuition since forever. And this is something that was lacking before. So that's it. Thank you for your attention.
Thanks, Ivan, for your very interesting talk. Start the questions for two things that I want to say. The first, that you attributed the equivalence between locally presentable and locally generated categories to the book of Rositzky and myself. That's unjust towards Gabriel and Ulmer. It's already there. No, but the thing that could interest you is that there is a concept that Stefan Milius, Larry Moss, and myself introduced called smooth class of monomorphisms in our book that's since eternity on the internet because it's never finished. But this is precisely your Aleph zero
conveniency.
Convenient. And we have two surprising examples. In complete metric spaces, the regular monomorphisms are Aleph zero convenient. And in metric spaces, both monomorphisms and regular monomorphisms are. So I just wanted to point that out. And now I'll stop my impoliteness and ask for other people having questions or comments. First in the audience, Walter.
Just for clarification, so your factorization systems are not necessarily proper, right?
No, I didn't, yeah.
Right, but nevertheless, you ask somewhere for equal powerness, which is okay. I just wanted to clarify that I understood that right. Okay.
Yeah.
Other questions in the audience?
Thank you for the beautiful talk, Ivan. So a fundamental property of locally lambda presentable categories is that if you have a lambda co-continuous and a functor of one, this has initial algebras. And I was wondering if in your notion of a locally lambda generated category has the same property.
Read our book.
So
It's
I,
there. And the answer is yes.
I expect the answer to be yes, yes. But we haven't proven it, and I wouldn't sign under this statement. But I expect the answer to be yes.
Thank you very much.
Yeah. Alexander, go on.
Hello.
Hello.
Yeah, okay.
Great talk, very interesting. I just want to comment on your remark right at the end that you've at last found a context in which compact Hausdorff spaces are compact objects. This is the second time I've heard this remark. The first time was Clark Barwick last year at the MSRI during a series of talks on condensed sets. He made the same comment about condensed sets being a context in which compact Hausdorff spaces are compact objects. I suspect for similar reasons, given the close relationship between condensed sets and compactly generated spaces.
Yeah, that makes sense. Thank you.
I don't know if that question is about the total of Paul Taylor.
Paul Taylor had a
Yes,
comment?
but the answer of Nathaniel is correct. The definition is new, well, to our knowledge, of course, and it is in the paper. Paul was asking whether the notion of convenient was well established. And to our knowledge, no, but Adamek was saying that they have a similar notion in some papers.
Yes, and definitely there is a close connection to this new notion, this pretty old notion in a preprint of Paul Taylor, where he is proving the general recursion theorem. So there is a close relationship.
This is definitely something I don't know.
Yeah, absolutely. There do not seem to be any other question. So let's thank Ivan again.
Thank you.